Welcome back. Today we're going to be discussing Chapter 9, Network Connectivity. In today's lecture, we're going to explain networking basics. We're going to talk about network topologies, networking hardware, packaging data in order to transport it, and how devices themselves connect to a network. We're also going to describe network transport and communications protocols, and determine which of these protocols are used in specific computer operating systems. We're also going to, last but not least, explain how we can integrate different operating systems onto the same network so they may communicate. Let's go ahead and get started. First and foremost, what is a network? Well, a network is nothing more than a system of computing and communication devices that are linked together with cables or wirelessly. In this diagram, we have combined both wireless and a cable network into a LAN. Now, all networks have hardware and software elements combined in order to provide this functionality. Some of the hardware components that we associate with networking components would be computers, printers. We have communications cable, such as Ethernet. And we have networking devices themselves, things like routers or wireless routers, switches, and occasionally you might even run into an old-fashioned hub. Now, there are software components that also make a network viable. We refer to a lot of these as software components. Client and server operating systems are one example. Device drivers, which allow the devices themselves to communicate. And of course, networking protocols are also a software component. Client and server operating systems. A client operating system enables a workstation to run applications, process information locally, and it will communicate with other computers and devices over a network. When we talk about a client operating system, we're generally referring to a workstation. That's a computer that actually has a CPU, and it can run applications locally or obtain applications and files from another computer on a network. A long time ago, terminals were quite common. A terminal has no CPU or local storage for running programs independently. The main use of a terminal is only to access the mainframe or a terminal server, including a server that may run 2008 or 2008 R2. Terminal Services is renamed in Windows Server 2008 to Remote Desktop Services, but it offers the same functionality. A server operating system coordinates network activities, authenticates clients to access the network, and enables client workstations to access shared network resources such as printers, files, or software. Generally, the hardware that runs a server operating system is far more robust than what you would normally see in a workstation environment. Security is an important function of a network, including the server operating system. There are different levels of security that should be implemented on any network. Now, this isn't a security class, so we won't go into that in detail. But, of course, one simple way to help secure a network, or particularly a server operating system, is to use logins and passwords. This is generally considered an industry standard, and we tend to refer to logins and passwords as strong or weak. There are many layers in security for a network. Another way that we could further secure a network or a server operating system is to use something called certificate services. Certificate services use digital certificates to verify that a user or an entity is trustworthy. Now, certificate services are particularly important on networks that tend to involve money or require the exchange of very sensitive data. Now, networks that are running Windows Server 2008 or 2008 Release 2 have an additional layer of functionality that we refer to as the Statement of Health, or SOH. Now, the SOH basically helps ensure that each network client connecting to the server is valid. And when we say valid, we're referring to the fact that that client is considered secure and is current on its operating system updates. As we know by now, operating system updates in and to themselves help ensure the security of the server infrastructure and the workstation infrastructure. Updates help patch issues that have been determined by the operating system vendor, particularly issues that may involve security breaches or ways that allow malware to intrude upon the operating system. Now, server operating systems also allow us as administrators to save time and money. One of these ways is by centralizing the installation of software and operating systems on client workstations. This is particularly important on large networking environments. Now, from Windows Server 2003 on up, we use something called Remote Installation Services, or RIS, to help install client operating systems such as Windows XP Professional or Vista or Windows 7 on a mass scale. Now, in Windows Server 2008 or Release 2, that installation service was updated, and we now call that Windows Deployment Services, or WDS. Now, WDS is used to mass install Windows client operating systems. We tend to think of operating systems now as Windows Vista and Windows 7. When you use RIS or WDS to install client operating systems on the network, you do this by basically creating an operating system image. That image is going to contain specific settings that you wish to have the users imprinted on their machines. And then the image is downloaded and installed on each of the clients. For example, if all the clients have to have a particular desktop appearance, we can create an image that is set up specifically with that desktop appearance so that it shows on all computers by default. Now, I can also, as a network administrator, enable Windows, XP, Vista, or 7 clients to install custom configured application software from a central Windows server. And I can do this via the client's local control panels. We refer to this as publishing an application. I can also assign applications to specific users or groups within my network using Windows Server 2003 or Server 2008. When we talk about assigning applications, what we're basically saying is that we can enable a particular client or group of clients to automatically start a particular version of software through a desktop shortcut or by clicking on a particular file extension. The great thing about assigning applications is it's done at the server level, and that means that if a user for some reason accidentally deletes a shortcut, no problem. It's automatically reinstalled the next time the user logs in. Now, when we talk about networks in general, we generally refer to local or wide area networks. We usually classify networks by their reach or their scope. How many users do we touch? In general, a local area network, or a LAN, includes a service area that's relatively small. This could be a network in an office area or building, or maybe one floor in a building. Depends on your infrastructure. A wide area network, on the other hand, tends to offer networking services which go over longer distances. We usually think about WANs as networks that span cities, states, or even countries. They often connect disparate LANs over a long distance. So an example of a WAN would be using a cable or a DSL modem at home to connect to your ISP, and that's going to connect you to other networks worldwide. This is probably a good time to talk about network topologies. Now, a topology, of course, is the physical design itself of the network, or the path data takes when it goes from one computer to another. The physical design of a network we generally refer to as physical topology, and the actual path the data takes when it goes from computer to computer, we refer to that as a logical topology. Now, a bus topology is generally considered a straight line approach to networking. It involves a central cable, which is generally referred to in a diagram as the straight line, to which all the computers and devices will attach with two endpoints that must be terminated to keep the signal from reflecting back along the path. A ring topology is a little different. The data carrying the signal goes from one station to another station around a logical ring like the circle of computers connected to one another. We usually don't think of ring topologies much being used in LANs, though we do find some in some larger WANs. Now, a star topology basically allows computers or devices, which we refer to as nodes, to connect to a central device, such as a switch or a wireless access point. Now, in a cable network, the switch sends the signal onto the segment that has the destination computer. Now, a star topology in today's networking environment is probably the most popular networking topology because it's one of the most flexible topologies. And a network can actually share different topologies as well. Here's an example of a star topology using a wireless access point as its central mode. Now, a star bus hybrid topology, like I said, we can combine them on a network, will combine the logical communications of a bus with the physical layout of a star. Each segment radiating from the star in this instance is the central connecting device, is like a separate logical bus segment. Devices or nodes on a network generally connect the network using a NIC card or network interface card. A network interface card is basically either built in the system or is something you can add to a device that will allow the device to connect to a network. Every NIC card will have something called a media access control or MAC address. And by now, after doing some of the labs that we've done, you should be somewhat familiar with MAC addresses. But a MAC address is defined as a unique hexadecimal address assigned by the manufacturer. Every NIC will have one. Another name for this address, of course, is the physical address. And when you go into the command prompt and you try to find the MAC address, it will be labeled physical address in Windows environments. Now, it's used in general like a postal address because it enables communications to be sent and received based on this address. Now, that address is going to be stored in firmware. It's going to be stored on the chip on the NIC card that contains the drivers or other software necessary for that NIC card to communicate with the operating system. It is established by the vendor, and I can actually use the MAC address to determine the vendor for a NIC card. All MAC addresses at this point have 12 digits. Now, here's an example of a network which is identified by its MAC addresses. As you will notice, each device has a unique physical address. Let's talk a little bit more about some other networking hardware that you may see. For instance, cables and wireless media. Cables and wireless media are an example of a communication medium. And the communication medium is pretty much anything through which data is transmitted. One example of cabling or wireless media you may run into is something called twisted pair cable. Twisted pair cable consists of one or more pairs of twisted copper wire bundled together within a plastic outer coating. Now, we twist those wires to help reduce electromagnetic interference, or EMI. We'll often refer to that as noise, by the way. And there are two configurations of twisted pair cable that are available: unshielded, or UTP, and shielded, or STP. Now, STP is indeed faster and it's more reliable because, well, it's shielded and that helps reduce the electromagnetic interference. But it's also a lot more expensive and it's pretty hard to move around. It's not very flexible. We usually use STP in places like wiring closets or somewhere where we've got a high voltage transformer, anywhere where we think the electromagnetic interference is going to be abnormally high in our building environment. However, UTP is most often used on LANs today. It is what you're going to run across more often than not, and it's generally what is going to run into the back of your NIC card. In addition to twisted pair, we also deal with coax cable or coaxial cable. Coax cable is really nothing more than copper wire surrounded by several layers for insulation. Now, we don't often see coax cable in LANs today. We often saw it in ring topologies. And it's mostly used today for home internet connections. Cable television often uses coax cable. Most connections are used by something called a hybrid fiber or coax HFC cable connector. Now, fiber optic cable you're beginning to see quite a bit of. Fiber optic cable consists of thin strands of glass that transmit signals using light. Fiber optic cable can transmit faster than copper and it's not prone to EMI at all. We often use fiber optic cable in businesses or on high traffic network backbones. Fiber optic cable is significantly more expensive than twisted pair, and therefore we don't see it usually inside building infrastructures. We usually use it for backbone infrastructure connectivity. Now, wireless transmissions are carried typically by radio frequencies or light through the air. Now that we've talked about some of the mediums that help transmit the data, let's talk about some of the devices themselves. We refer to devices that help transmit media through the network as network devices. Network devices are used to connect computers and network attached devices like printers to each other and to connect networks together. Hubs were once popular network devices. They've typically been replaced by switches in most networks. Occasionally you may see a hub. One of the differences between a hub and a switch is that all communications that go through hubs are broadcast to all segments that are attached to the hub. That means when a signal hits the hub, it is duplicated to every port on that hub. A switch, on the other hand, is intelligent. It will only transmit the information onto the segment where the destination device is located. That helps save bandwidth on the network, or how much data is transmitting on the network. Now, a wireless access point is also a piece of networking hardware. It connects wireless devices to a wired network. The wireless router in your house would be one instance of a wireless access point. In businesses or large buildings, you may see many access points connected to each other to help form a seamless network environment. Bridges have often been replaced by switches as well. Bridges were typically used to extend segments or link segments that use different cable types. You probably won't run into too many bridges on networks today. Routers, on the other hand, are everywhere because we use routers to connect networks. Routers generally represent an entry point into a network. Now, in addition to the important function that routers have for disseminating where traffic goes onto a network, or whether it leaves the network, it can also be programmed to act as a firewall. A firewall is hardware or software that can secure data from being accessed outside a network, and it can prevent data from leaving a network as well. We do this typically by configuring port settings on the firewall. And once again, this is not a security course, so we won't go into this in detail. But it works very similarly to a physical firewall that separates building components. A router also keeps tables of network addresses along with the best route to other network addresses. You can't talk about networking unless you talk about packets, frames, and cells. Each network device translates data into individual units and then places the units onto network media for transmission. That's how data is sent. Now, we refer to these data units as a packet or frame. There is a difference. A packet contains routing information that will allow the packet to be forwarded to specific networks. A frame, on the other hand, contains information about the specific sending or receiving device. Here's an example of a basic packet format, with a header with the source destination and the routing information attached to the variable length data, and then a footer with the error data attached. A cell is nothing more than data units that are designed for high-speed communications. A cell has a control header and a fixed-length payload. Now, a payload, while we're talking about payloads, is a portion of the frame, packet, or cell that contains the actual data that we're concerned about sending in the first place. One element of the cell header is path information that will enable the cell to take the route through the network that is most appropriate for that type of data. It's important to note that the exact format for a frame, packet, or cell will be determined by the type of protocol used on a network. Speaking of protocols, a protocol is the set of formatting guidelines for network communications. We refer to it kind of like a language, so that data sent by one computer can be read by another. We use protocols for communicating transport of packets and frames among network devices. We use protocols for encapsulating data and communication control information, and for providing communications to accomplish a specific function, including things like flow control. Protocols are responsible for enabling communications over a long-distance network, or enabling remote users to dial into networks. And protocols are used for transporting test, network status, and other network management information. Standards for network communication were established by something called the Institute of Electrical and Electronics Engineers, or IEEE, through its 802 Standards Committee. Now, 802 standards are followed by network administrators and manufacturers to ensure that network devices will be able to communicate with each other, We refer to that as AO2 compliant. Now, Ethernet is a type of protocol. Only one station on a network segment can transmit at a time with Ethernet. When more than one station talks at the same time, we refer to that as a collision. Ethernet uses carrier-sense multiple access with collision detection to perform that function, or CSMA-CD. Now in CSMA-CD, the NIC card listens to see if another device is transmitting. If it doesn't hear any transmission, then if it has something to transmit, it's going to transmit. Now, if two devices on the same segment try to transmit at the same time, a collision occurs and then both the transmissions are dead. So when that happens, a jam signal is sent to warn the other stations. Each device waits for a different amount of time before attempting to transmit again. Now, the typical speeds that are supported today are 100 megabits per second, we refer to that as fast Ethernet, and 1 gigabit per second, or gigabit Ethernet. Now, 10 and 100 gigabit per second Ethernet are generally used on Ethernet backbones. Ethernet is probably the most commonly used transmission protocol that we use today in our networks. Now, in wireless communications, the most prevalent protocol used is the carrier sense multiple access with collision avoidance, or CSMA/CA. Now, this is a variation of the CSMA-CD method used in Ethernet communications. Basically, the way it works is when a wireless station wants to transmit, it will listen to other transmissions. If there are transmissions, it will wait a specified amount of time and then listen again. Now, when the transmissions cease, the station will then begin transmitting. And there are four main IEEE wireless specifications in use today. 802.11a with a frequency of 5 GHz can send up to 54 megabits per second worth of data. 802.11b uses a frequency of 2.4 GHz and sends up to 11 megabits per second. 802.11g uses 2.4 GHz frequencies and it can send up to 54 megabits per second. And then the newest member of the wireless family, the 802.11n, uses either 2.4 or 5 GHz for their frequency and can send anywhere from 100 to 300 megabits per second. Now, a transport protocol is interfaced with an operating system through three basic elements: a network driver specification built into the operating system, a NIC, and of course the NIC's driver. Network operating systems are built to offer special elements which programs call hooks in operating system kernel that will enable the operating system to interface with a network. Now, an example of that is Microsoft and 3Com Corporation designing the Network Device Interface Specification, or NDIS, and the Windows-based NDIS drivers for this purpose. Now, one way to think of networking hooks in an operating system and how a NIC driver links into those hooks is by using an analogy that you'll find in your book of the lock and key. The combined hooks are like a lock, and then of course the NIC driver software would be the key that is specifically cut to exactly match the unique configuration of that lock. Now, Unix and Linux operating systems are compatible with the NDIS driver through using open source software, something like NDIS Wrapper, and Mac OS X is also compatible with NDIS. Now, if you're going to be purchasing a NIC card, there's some things you need to think about. For one thing, the NIC cable interface on the card must match the type of cable being used on the network. And of course, if there's no cable needed, you can go with a wireless NIC card. Make sure that the current driver is installed for that NIC card to support that works with the operating system. And after the NIC is set up, the operating system, NIC, and the driver handle the work of converting data to an Ethernet or wireless format for transport over a network, using the same three elements that enable receiving and interpreting the data as well. Communications protocols are responsible for carrying data between two communicating devices. And today, all operating systems, or at least the ones that we discuss in our book, use TCP/IP family protocols, same protocols that were developed for use on the internet. Now, TCP/IP was developed in the early 80s for use by the U.S. Department of Defense and Advanced Research Projects Agency Network, or ARPANET. Let's break down TCP/IP into the two basic elements and talk about them. Now, TCP, the first set, Transmission Control Protocol, is responsible for establishing the communication session between two computers, and it ensures that the data transmissions are accurate. It encapsulates, transmits, and receives the payload data, and it closes the communication session between two computers. Internet Protocol handles the packet addressing. It also handles the packet routing, and it's responsible for fragmenting that packet as needed for transport across different types of networks. IP protocol also provides a simple packet error detection in conjunction with the more thorough error detection provided by TCP. Now, TCP/IP comes in two versions today: IPv4, and IPv6. IP version 4 is the most commonly used today. Now, it has a limitation when it comes to address allocation. And the world is, last time I checked, it's out of IP addresses, or close to it. Now, IPv4 uses a dotted decimal notation that consists of 4 8-bit binary numbers separated by periods. You know these as IP addresses. There are 5 classes of IPv4 IP addresses. Let's talk about each of these in a little detail. Class A is assigned to large networks, the largest networks available. Now they can have, each one of these networks, that is, can have 16,777,216 modes. That's a lot of computers on a network. Now, a Class A network address example would be 122.0.0.0. A Class B network is typically assigned to medium networks, and it can have up to 65,536 nodes. A Class B network address example would be something like 132.155.0.0. A Class B network could be, say, a college or university, something that has a fair number of computers attached to it. A Class A network may be something like an ISP. A Class C network, on the other hand, is assigned to small networks, and it can have up to 256 nodes. An example of a Class C network is shown here, 220.127.110.0. In addition to these 3 assigned classes, we also have 2 additional classes, Class D and Class E. Class D is used for multicast, which is sent to multiple nodes, and Class E is used for experimental purposes. Now, 255.255.255.255, we refer to that as the broadcast address, and that is sent to all nodes on any particular network. This table, 9-3, shows a breakdown of each of the 4 particular addresses, as well as their ending addresses. Now, a newer way to assign IP addresses is through something called classless interdomain routing, or CIDR. Now, CIDR ignores address class designation. CIDR provides more IP addresses for medium-sized networks. And an example of CIDR would be 165.100.0.0/14. A subnet mask is used to identify networks or subnetworks, i.e. the subnet, within a larger network setup. On large networks, subnets can be used by an administrator to create smaller networks to limit network traffic congestion and to provide security on network segments. Here's an example of using TCP/IP subnet masks. In this instance, we have broken down this network into 4 separate subnets. And I can use subnets to help reduce the traffic between each of these different segments. Additionally, I can go in at the router or switch level and set up specific security protocols for each of these segments. Computers and network devices that use TCP/IP protocols have 2 addresses. The MAC address, which we've talked about earlier, which is the address that's burned into the NIC card, and the IP address, which is going to be assigned by the network administrator. Now, IPv6 is new. It's a TCP/IP version that uses 128-bit addresses to solve the shortage of the IPv4 address situation. Now, IPv6 or IP version 6 provides a more specialized networking implementation such as voice, video, and multimedia applications. And all new operating systems today do support the use of IPv6. This table outlines some additional communication protocols that you will typically find on a network. For instance, Routing Information Protocol, or RIP, enables network routing devices to build tables of routing information about the location of particular networks and networking devices. SMTP is what we use to transport email over networks and the internet. File Transfer Protocol, or FTP, is something that we use to send or receive files typically over a network or the internet. Telnet allows us to use a computer to emulate a terminal for connections to other computers. Hypertext Transfer Protocol, or HTTP, well, we should all know that we use that as the default web communication with web browsers. Point-to-point protocol, or PPP, enables the computer to remotely access a network through dial-up modem connections. Simple Network Management Protocol, or SNMP, is used to detect and track network activity, including network problems, used by network managers to monitor and manage TCP/IP networks. The Internet Control Message Protocol, or ICMP, enables us to report network errors, including utilities such as the ping utility, to test network connectivity. And of course, we have the DNS, or Domain Name Service, which resolves domain and computer names to IP addresses. Without it, we wouldn't have things like www.google.com. We'd have to know 8.8.8.8. Dynamic Host Configuration Protocol, DHCP, well, we use that to automatically assign IP addresses by a DHCP server. DHCP is used in Windows, Unix, or Linux environments. There are 3 steps involved in setting up a communications protocol in an operating system. First, you have to install the protocol in the operating system. Then you're going to have to bind the protocol to the NIC card. Last but not least, you're going to have to configure the protocol communication parameters. Now, typically, installing and binding a protocol is combined into one procedure, and it's usually an automatic procedure when you install the operating system. Binding enables the NIC to format data for that protocol and identify the most efficient methods for transporting it. Configuring a protocol, which is the third step in the process after installing a binding, is done to configure the protocol communication parameters. Now, the parameters to configure include some or all of the following: configuring an IP4 address and/or configuring an IPv6 address, specifying the subnet mask, also called the net mask, designating a default gateway. That's the device that will link the network to other networks, including the internet. Specifying a preferred DNS server. Well, that's going to provide the lookup of IP addresses and the computer device names. And of course, specifying an alternative DNS server when the preferred one is busy. We can also use Dynamic Host Configuration Protocol, or DHCP, to automatically assign IP address information to computers. Now, there are a couple of advantages to DHCP if you can use it. It's not necessary to assign IP addresses manually, and it will ensure that no two computers are assigned the IP address. There are instances where using DHCP is not appropriate, such as on servers or print devices. Now, automatic private IP addressing, or APIPA, is available in Windows XP, Vista, 7, Server 2003, and beyond. If automatic addressing is selected but there's no DHCP server on the network, the operating system itself will assign an IPv4 address from a reserved range in the 169.254.0.1 to 169.254.255.254. Some computers and devices must have an IP address that is manually assigned and never changes. Like I said before, servers, print devices, switches, routers. We call this a static IP address. Now, static IP addresses are important for devices that will be well known on the network or used by other devices for services. These are devices that other devices are dependent on in order for the network to function properly, or to ensure that you're able to exchange data reliably. Print servers, file servers, switches, all of these devices should have static IP addresses. Now, most Unix and Linux operating systems, it's important to note, will have TCP/IP networking support built in. Some will automatically run a network configuration program when you first boot the computer. Now, in Unix and Linux, if for some reason that automatically does not work, then you can configure it later by using the ifconfig command in Unix and Linux. And in Mac OS X Leopard and Snow Leopard, these configurations are going to be made using the network option from the System Preferences windows. Here's an example of Airport in order to configure a wireless network connection in Mac OS X Snow Leopard. Notice the IPv4 address, 192.168, which we know by now is a private network address. The subnet mask of 255.255.255.0, which indicates it's a fairly small network. A router is assigned to this, 192.168.0.1. And it's set to configure IPv6 automatically. Okay, as promised, one of the last things we'll talk about today is integrating different operating systems on the same network. The key to implementing multiple operating systems on one network is basically to select a transport protocol and communication protocols that will be supported by all of the operating systems on the network. Now, Ethernet is particularly well suited to a network that has different operating systems. As I said before, it's supported by Mac OS X, Unix, Linux, Windows-based operating systems, all the server operating system we discuss in the book, and even mainframe operating systems will support Ethernet protocol. Also, the TCP/IP communications protocol is supported by most operating systems today. You will rarely go wrong if you include these two protocols in a network that has to integrate different operating systems. Okay, that's pretty much it for today. Let's do a brief summary. A network, as we said before, is a system of resources and productivity tools that communicate with each other, enabling us to share information over short and long distances. Now, networks are going to be categorized basically as either a LAN or a WAN, depending on their scope of service. LANs generally are going to cover a building or floor of a building, a small area. A WAN, on the other hand, will be considered a long-distance network. It's typically going to join LANs and individual users. Now, networks are designed in standardized topologies. We've named those today. Bus, star, ring, star-bus hybrid are the topologies generally in use. And they use standardized communications by means of frames, packets, and protocols. Now, a protocol in and to itself are important to network communications because they act as the common language for communication between devices and provide reliability, delivery of data, and they monitor networks for problems. Modern computer operating systems use TCP/IP. Now, this is pretty much the de facto communications protocol for networks and the internet today. Now, IPv4 is in the greatest use today, though we're beginning to see IPv6 take hold. Why? Because it offers a greater range of addresses. It also provides better security, and there's some other network improvements associated with IPv6. Networking devices such as hubs, bridges, and switches, and routers enable network connectivity. Now, hubs and bridges are basically becoming obsolete. You're not going to see too many of those around anymore. But switches and routers are the de facto standard on the network. Each device is used to achieve different connectivity goals based on its capabilities, however. Now, cabled Ethernet and wireless networks are used separately, and they're also combined to enable flexible networking. Windows operating systems, Unix, Linux, Mac operating system 10, all are going to offer tools for configuring the TCP/IP communications protocol. That will include the IP address, the subnet mask, the gateway, and the DNS parameters, all of which are needed to have successful connection to the network. And current Windows operating systems, Unix, Linux, Mac OS X, Leopard, Snow Leopard, can be integrated on the same network because they will all support TCP/IP and their default communications protocol and are compatible with the Ethernet. That's all I have for Chapter 9. And I hope you have a good day. Thanks a lot.